Hey guys, in this new chapter we're looking at circle theorems, and I want to kick off with just looking at the different parts of a circle. Some of them you are quite familiar. So here we have the circumference. It's looking more like an oval at the moment. Maybe if I can do a little bit better. And then you have the middle of the circle, we have the radius, which is there, and then if we go all the way through, we have the diameter. Okay, some other parts of a circle that you may not be familiar with. If you have a line going from one point to another point of the circle, but not through the center, that is going to be considered as the chord. Okay, and then the space that is in that segment is what you call a segment. Okay, so this is called a segment, but the thing is, if we were to change the colors, okay, so I'm going to erase that part, but that part is also a segment. Okay, so this is a minor segment, and this is a major segment. Okay, so two segments of a circle that's been divided by a chord would probably be the best way of explaining it. Okay, so now we'll move on to some other aspects, and you would be familiar with dividing your fractions, your circle into fractions like a pizza. Here we have what we call a sector, and the same thing is that this remaining area is also called a sector. Okay, what's the difference between the two? Well, this is a minor sector, and this is a major sector. Okay, so obviously the bigger part is the major one, the smaller one is the minor one, just similar to what we did with major and minor segments. Okay, so once we've looked at that, I'm just going to keep this section here. But what I want to pinpoint is that this line here is what we'll call an arc. And then we choose a different color. This remaining part here is also an arc. Okay, this one will be a major arc, and then this one is a minor arc. And then lastly, I want to look at two more parts of a circle, and I'll just use a ruler this time for this demonstration. And any straight line that touches a circle at one point, this is what we call a tangent. And then the last part is, if we already know that this line is called a chord, but then if we were to extend the line outside of the circle, then this is now called a secant. Okay, we're going to move on to different relationships of angles within the circle with all these different features and lines that we've just looked at. And hopefully you'll find some patterns and some interesting things. Okay, so here we are at this site, greatmathsteachingideas.com /circle-theorems/. Just a very good interactive tool rather than just, reinventing the wheel. Now these theorems, I guess there's no real order or sequence, just like the index laws. There are a number of laws, whether 1 or 5, it's really up to you, just as long as you're familiar with each of them. Here we have a line that goes right through from one point to the other, so that's your diameter. And if we create a triangle with that, at any point that we decide to change that triangle, notice that the angle is always at right angles. So that's the first rule, okay? And you could change wherever this diameter is, and this is using GeoGebra, so the size of the circle gets changed. But if we can, it doesn't really matter where the diameter is because it's always going through the center. This point here, making a triangle, will always be 90 degrees. So that's the first part that I'd like you to take down. Okay, the second one is that we have a look at this. Again, different diagram. If you look at this part here, we're no longer at a diameter, but this is now a chord. And so if you make two triangles, you'll see that the angles in the triangle will always be the same, regardless of where that chord is. The moment that you change the chord, the two angles will obviously differ. Sorry, be changed, but they will be identical still. So those two triangles, regardless of what chord it is, will always be identical. Let's move this around to making two triangles and through a chord. So 61, 61. It doesn't really matter where I move that point, just like what we had with the previous example. So imagine this was a chord. This singular triangle would always have the same angle, but because it's going through the center of the circle, it's always 90 degrees. But because it's not going through the center of the circle, that angle doesn't change, obviously, but it's all dependent on where the chord is. Okay, so let's move on to the next theorem, is that when you'll see this arrowhead, obviously this doesn't change again going around. If we have a chord that going across from 2 points of a circle, this doesn't change in terms of angle, like what we've seen in the past two theorems. But what I'd like you to take note is when you do have another triangle that connects that same chord to the center of the circle, this angle is always going to be double the size of this angle here. And so if we move this to that point, so we've changed the position and the size of the chord, the angle obviously gets bigger. We've got 110. This angle here becomes 55, so it's half the size, or you could say this is twice the size of this angle over here. Again, if we were to change it, we've got 144 degrees here. Half of that is 72. That doesn't change. We can make it smaller. And then obviously 38 degrees is half of 76. So that's that theorem that I'd like you to take note of as well, that pattern, that occurrence. If we end up having four chords and we make a quadrilateral, then we will have what we have diagonally opposite supplementary angles. Okay, so supplementary angles are two angles that add up to 180 degrees. And so we find here is 79 plus 101 is 180. 92 plus 88 is 180. So if we move this around, and it doesn't matter where it is, it's kind of looking a bit like a trapezium. But within the circle, the context is 66 plus 114 is 180. 66, oh well, again, here they are just the same here. If I move this, 81 plus 99 is 180. Moving this around, let's change everything. Here we got 82 plus 98, 180 degrees. 105 plus 75, again, 180 degrees. So there's another theorem. Next one, what we have here is when we have two chords that cross over each other, or intersects or bisects. Bisects is when they cross over in the midpoint, okay? And they are perpendicular. And it doesn't matter where it is. Notice that when you're going to cut things into two, the other chord is obviously going to go through the center of the circle. It's always going to cut that chord in half at 90 degrees. So we're moving these around, and then because it is bisecting into two parts, you would expect that this length here, so BD, is going to be the same length as DC. Okay, so make it a little bit clearer here. we've got C to D is 32, and then B to D is 3.2 and 3.2 as well. Okay, still cutting at 90 degrees. So those lines are bisecting at perpendicular angles. Okay, so here we have an angle between a tangent and a radius. So here we got a tangent. Tangent is that line that touches one point of the circle, and then we've got the radius. When they touch each other, it is going to be at 90 degrees as well. So no matter where you put that tangent, if you make the radius touch that tangent at that same point, it's going to be 90 degrees. Okay, so you could apply the same thing here, I guess. If you move this chord all the way around to the tangent, you end up having 90 degrees. And then the next one here, if we have two tangents meeting at one point outside the circle, you are going to have the same length of line going from the point where the tangent touches the circle to the point that the other tangent intersects. Okay, so we have point D and point E. They are the point that these two tangents are touching the circle, and when they cross over each other, that these two lines, so CE and CD, are both going to be the same length. And then we can move this around. Same thing, you can see that both those values are exactly the same no matter where we put that point. And if we go around or if we extend it, they are identical. Okay, going right down to something really close, CD and CE is equal to 1, and then we can make it as big as we want and extend it further outside of this window. Okay, next one here, we have alternate segment theorems. This is where we look at some angles here. We've got a triangle in the middle that's composed by 3 chords. And what we can see is that the alternate segments, remember, a segment is part of a circle that's been, I guess, segmented. I don't really like using the same word to define another one, by a chord. So here we have a tangent. Okay, so the tangent cutting the touching the one point of a circle and creating a angle of 40 degrees with the chord. Okay, now the angle over here is also 40 degrees, as well as that angle there. This angle here on the other side, 67, is also the same as this angle over here. And doesn't really matter where you move these 2 points or where you move the point where the tangent touches, it's going to reflect the same values. So 72 and 72, 37 and 37. Move this around, 37 is going to go around. Remember, when you have a chord, this triangle, this angle here at the apex is not going to change in size unless I change the size of the chord. Then all of a sudden this changes also. And then same thing, if you move this around, you'll notice that the opposite or alternate angles, so 54 is the same as that angle, and just managed to have all 4 angles to be exactly the same thing. Now, if you think about this, the only reason why these 4 angles are the same is when this chord is parallel to the tangent. Okay, so you can see the letter Z, so that means that 54 is alternate angles to that angle, and this angle is alternate to that angle. But the moment that I change this point on the tangent, this chord here is not parallel to the tangent. However, the alternate angles that reflect the same angles actually changes. So this angle here, that is going from the minor segment to the tangent, is 36. That is the same as this angle on the left. And same thing, the other angle that touches the tangent 70 degrees is going to correspond with that angle up on the top. Now, before I move on to an example that will apply some of these theorems together, something that I forgot to mention is that if we had a line going all the way through the center of the circle and touching the point of C, and then you have the radius going from the center to point D and the center to point E. So we would have one triangle from the middle. So let's call this point O. So ODC, that triangle there, is going to meet at right angles. And the same thing with this one. So from OEC, that's also right angles. Okay. So it's applying the same theorem as this one, where any point, any radius that's touching the tangent is going to meet at 90 degrees. And then this theorem here, where the line going through the center of the circle is going to bisect the chord into two parts. Okay, so we will have the same part here where we'll end up having two identical triangles from the top and the bottom. Or if I'm going to put point C up on the top, then we'll have a line going right through. The triangle on the left is going to be identical to the triangle on the right. And those 2 points or those angles is going to be at 90 degrees. Okay, well, let's move on to an example. And with all of this, just practice will help you make yourself a bit more familiar with what to look out for and how to apply these different theorems. Okay, so here's a diagram with a lot of lines going all over the place in this circle. And it will look a little bit confusing, but just like any geometry, any measurement, or any other puzzle, you'd want to just take it one at a time. Take it slowly, don't rush things, and see what you can solve piece by piece. The first thing I can see here is that we've got a right angle there, and this is the radius, and here is the radius as well. So if these two sides are the same, then we could automatically assume that these two are the same. It's an isosceles triangle. So S is equal to T, and a triangle adds up to 180 degrees. And if this is 90, then each of S and T must be 45 degrees. Okay, that's the first part. Now, the other part that I can already see is if this angle here is 90 degrees, this angle is going to be half of that. Okay, so N is going to be 45 degrees as well. Next thing is that this side, or this line going across, if we were to go all the way through, this is a tangent, and so therefore this angle has to be 90 degrees. Okay, so the diagram doesn't look like that, but this is where I guess you just need to apply your theorems and understand what's going on. So that means if S is equal to 45, then R needs to be 45 degrees as well, because they both add up to 90 degrees. Okay, then if that's the case, if this is 45, we can then solve for this angle here. 25 plus 45 plus whatever, let's make this angle Y. That needs to add up to 180 degrees because we have a triangle here. What we'll have is Y is going to equal 110 degrees. 25 plus 45 is 70, so the remainder is 110. Then what we'll have is we'll have that angle all the way around to be 180. So we could say that T plus M plus Y is 180 degrees. We know that T is 45. We know that Y is 110. Therefore, M must be 25 degrees, which is what's left over. The final angle that we need to work out is angle U. And because this is 90 degrees, this should be 90 degrees. We also know what M is. So therefore, 25 plus 90 plus U is equal to 180 degrees. And then U should equal 65 degrees as remaining. Yeah, so hopefully that helps you. Got any questions? Let me know.